So where we left off was example 5, comparing methane, CH4, and ammonia, NH3 in terms of molecular shape and geometry. So if we take a look at methane, CH4, it looks like this. It has 4 substituents that are all hydrogen around a central carbon, and it is a tetrahedral shape. The reason for the name tetrahedral is the fact that if you connect all of the hydrogens to one another and create faces, you create a tetrahedron that has 4 faces. Each one of the CH angles, so between hydrogen, carbon, and hydrogen, is 109.5 degrees. NH3 has also 4 substituents, but one of the substituents is a lone pair of electrons, and being delocalized outside of a chemical bond, it pushes all the other chemical bonds away from it, containing electrons as well. That is a anionic electron repulsion, hence VSEPR. The result is bond angles that are less than 109.5 degrees. We call this geometry trigonal pyramidal because there are 3 atomic substituents, so that's the trigonal part, but it is not planar as the electrons are pushing everything away. Here are a few examples of substituents around a central atom. If you have 2, it'll always be linear. If you have only 3 with no other electrons above or below, like BH3, you can have something that's trigonal planar, tetrahedral with 4 substituents. 5 substituents can be something like trigonal bipyramidal, and 6 substituents can be something like octahedral. Of all of these exampps, we have 2s, 2p, 2p, 3p, 3p atoms. Only carbon, this 2p atom, obeys the octet rule. All of the other ones can violate the octet rule easily by being hypervalent in the situation of phosphorus or sulfur, or being subvalent, which is the situation for boron and beryllium. Below, we have our first example of a practice exam problem. These are going to be posted to OnCourse from now on. This is the only one that appears in your notes, but I will be posting problems and answer keys to give you some additional practice beyond problem sets, something that you might see on an exam. And this is draw the Lewis structure for CO, carbon monoxide, and find the formal charge on each atom. So here we have a triple bond that must exist between carbon and oxygen with a lone pair on each atom. That gives each of these 2p elements a full octet. And once the full octet has been achieved, you can calculate the formal charge and discover that carbon has 1 more valence electron than it's supposed to, so it's anionic, and oxygen is without an electron that it's supposed to have, giving it a more positive charge. And now, let's move on and continue our discussion about molecular polarity. So the polarity of compounds and covalent bonds is determined by calculating the difference in electronegativity between the 2 atoms. So something that is considered polar exists in a covalent bond where the difference in electronegativity between the atoms is about 0.5 or greater. Once you have polar covalent bonds, you then have to decide whether or not the molecule is symmetric or not. If it is asymmetric, and it has polar covalent bonds, then it will have an overall polarity and it will be polar. If it is a perfectly symmetric molecule, it will not be polar regardless of whether or not there are polar covalent bonds. So, for example, let's take a look at boron trihydride, BH3. Previously, we had drawn it like this, but you can also draw it sideways to show that it's trigonal planar. That is the shape, trigonal planar. Boron and hydrogen are only 0.1 electronegativity apart, so we do not have any polar covalent bonds, and it is symmetric, so it is nonpolar. We don't even actually have to analyze this compound in terms of the difference in electronegativity because it is perfectly polar, so there's no way that it can be, it's perfectly symmetric, so there's no way that it can be polar. In the next example, we're comparing methane, ammonia, and water. So here we have methane and ammonia again, and now here we have water given its bent structure. In methane, the electronegativity of carbon is 2.5, hydrogen is 2.1. So the difference there is 0.1. That is less than a difference of 0.5, which means that we do not have polar covalent bonds. If we don't have any polar covalent bonds, we cannot have a polar compound. This is also perfectly symmetric, so there's no way methane can be polar. In ammonia, we have a nitrogen, which has a 3.0 electronegativity, and hydrogen is 2.1. They have a difference of 0.9, making for 3 polar covalent bonds. Each one of them has a dipole arrow, showing that there's electron density being donated into the nitrogen. This molecule is overall asymmetric with an overall dipole heading in the up direction, the way that it's drawn, showing that there's more electron density at the top of the molecule. So we have a polar covalent bond, we have a polar molecule. Finally, over here with water, we have a difference in electronegativity that's very large, considering the oxygen is 3.5. So we have dipole arrows showing that electron density is being donated into the central atom, and an even more of an overall dipole heading in that direction. We have a very, very polar compound here. That leads to water being very sticky with itself and creating hydrogen bonding. If you cannot remember electronegativities, there will be a chart provided for you, but a simple test is that carbon, nitrogen, and oxygen go in order along the periodic table. It goes C, N, O, and then F would be furthest to the top right. Fluorine has an electronegativity of 4.0, oxygen 3.5, nitrogen 3, carbon 2.5. So they decrease by 0.5. All of the transition metals and all the metals are less electronegative. So that is a quick shortcut, which really is most of the electronegativity knowledge that you need for the periodic table. The main group is more electronegative. They're separated by 0.5, and metals are less. In example 8, we see a resonance structure for the nitrate anion. And here is one Lewis structure drawn. Nitrogen has an electronegativity of 3, and oxygen has an electronegativity of 3.5. So we just barely have polar covalent bonds in this molecule. After drawing the Lewis structure and filling in electrons to give each of these atoms an octet, as they are all 2p elements, we then evaluate the formal charges to discover that the oxygen at the top has a neutral formal charge because it has 6 electrons around it, which is exactly how many valence electrons oxygen has. Nitrogen has only 4 around it, giving it a positive charge since it's supposed to have 5. And the 2 oxygens at the bottom have more electrons around them than it's supposed to have. Each one of these has 7 in the immediate vicinity. Oxygen's supposed to have 6, and so each of them is anionic. However, nitrate does not really exist as one structure. It exists as a resonance hybrid. And when you draw the delocalization of all the of all the electron density spread around the entire molecule, we can see that we have polar covalent bonds taking electron density slightly away from the central atom, and it's all uniform and symmetric. So even though we have polar covalent bonds, we overall have a symmetric molecule, which makes nitrate non-polar.